All right, hi everybody. Continuing with section 4.1. We have another example. In a study of US high school drivers, it was found that 3,785 texted while driving during the previous 30 days and 4,720 did not, based on data from blah, blah, blah. Based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. Okay. All right, so as a reminder, I think for this we're going to use what we call the classical approach for probability. So when you have equally likely outcomes, and the people in this study would be the equally likely outcomes. I have a few thousand names of the people in this study. So when you have equally likely outcomes, the classical approach just says the probability is the number of ways getting the outcome that you're looking for divided by the total possible number of outcomes. So really the only thing you have to do in this problem is figure out how many people there were total in the study. Okay. And you're just going to do that by adding the 3,785 plus 4,720. Okay. So that's going to look like this. All right, summarize the information in a format that allows clear understanding. So you had 3,785 who texted, 4,720 who did not. So there must have been 8,505 total people in this study. Okay. So again, using the classical approach, we're going to say the probability that the selected driver texted while driving is going to be the number of people who texted, 3,785, divided by the total number of people, which is the 8,505. Okay. All right. So a little ways back in the last video, in part 1, it talked about what kinds of ways to write your answer. And their recommendation is either as a simplified fraction that's easy to understand. Now, I can tell this fraction has not been completely simplified. I could simplify it. I have a feeling it's not going to simplify down that far. So probably the easier thing to do is just ask the calculator what's 3,785 divided by 8,505. It'll change it to a decimal. And then remember, the rounding rule for probability is 3 significant digits. Okay. So sometimes in a probability, you have a few zeros after the decimal point. Those don't count. Significant digits start with the first number after the decimal point that is not a 0. Okay, so this would be 3 significant digits. Okay, so the probability that a high school driver is randomly selected, he or she texted while driving, is about 0.445. So there's about a 44.5% chance of picking someone who texted while driving. All right. Oftentimes it's helpful to talk about the complement of an event. That is the, so the complement of event A, which is denoted in your book like this, A bar. Different books have different ways of writing this. Consists of all outcomes in which event A does not occur. So if I was going to summarize complement in one word, it would be the word not A. Okay. And that's helpful because sometimes when we're looking for the probability of a certain event, it's a lot easier to figure out the probability that that event does not happen. Okay. So you're going to see examples of that. Okay, this looks familiar. You would have seen this at the end of the last video of part 1. In a recent year, there were 3 million skydiving jumps and 21 of them resulted in death. Find the probability of not dying when making a skydiving jump. Okay. All right, so the way we're going to do this for now, and we'll have a slightly different way later, is we're going to say, okay, there are 21 unfortunate outcomes in which the person skydiving doesn't make it. Well, that means there are 2,999,979 jumps where it turns out fine, okay? It seems kind of silly to be this precise. I mean, that 3 million is definitely rounded off, but anyway, it's what we have, okay? So the probability of not dying when skydiving would be that 2,999,979 over the 3 million total skydiving jumps. And as a decimal, that comes out to 0.999993. Okay. Now, technically speaking, I guess they are not using their own 3 significant digits rule. And I think there's actually a really good reason for that. If you just went with 3 significant digits, that would round off to 1. I think this is a better answer, okay? So don't treat that 3 significant digits thing as a hard and fast, you know, oh, I have to do it that way or else. It's just kind of a guideline. And I've told you before, I am personally not picky about rounding. If you're doing something for me, I am not as picky as, for example, you know, my math lab, okay? All right, so there is like a 99.9993% chance that if you skydive, it'll be just fine. That's not quite good enough for me. Won't catch me skydiving, all right? Okay, let's see. Rare event rule. This is going to, oh wait, no, I'm sorry, I'm thinking of something else. How do I explain the rare event rule? Suppose that you're playing with a pair of dice, okay? You know, regular, ordinary board game, 6-sided dice. And so we will maybe be doing some problems with dice later. So for example, the probability of rolling a 7 when you roll a pair of dice should be about 1 chance in 6, okay? So if I have a pair of dice and I roll them 100 times and 7 comes up 62 times, all right? That is really, really, really unlikely to happen by chance because it's only supposed to happen about 1 time out of every 6. So if I rolled the dice 100 times, I would expect about 16 or 17 times it would come up 7. If it came up 762 times, I would think, you know what? Maybe this isn't an ordinary pair of dice. Maybe there's something else going on here. So that's really what the rare event rule is about. It says if under a given assumption, the probability of a particular observed event is very small, like rolling 762 times, and the observed event occurs significantly less than or significantly greater than what we typically expect, we conclude that the assumption is probably not correct. So in my little example, my assumption is I'm playing with an ordinary pair of dice in which I would expect 7 to come up about 1 time out of every 6, okay? So if it came up 62 times out of 100, I would say that's probably not the right assumption. Maybe, you know, maybe I've got dice that have the same number painted on a few different sides, and so that makes 7 come up a lot more often. That's kind of what the rare event rule is about. Okay. Okay, using probabilities to determine when results are significantly high or significantly low. Okay. So when they talk about successes, the word success and probability means something a little different than what it means in everyday English. And probability of success just means the outcome that you're interested in. It may be a good outcome, it may be a bad outcome, it's just the outcome of interest, like rolling a 7, okay? So if, let's say I roll 62 7s in 100 times rolling the dice, I would say that is definitely a significantly high number of successes because the probability of that happening, I'm not prepared to show you this right now, but that probability would be a lot less than 0.05, okay? All right, so if the probability of the thing happening that many times is less than about 0.05, then we consider that to be a significantly high number of successes. Okay, and the same thing goes for significantly low. If I rolled a pair of dice 100 times and 7 only came up twice, that's probably not very likely. The probability of that happening is probably less than 0.05. Okay? So I would say that 2 would be a significantly low number of 7s if I'm rolling a pair of dice 100 times. Okay, so to recap some of the things we've talked about so far, the probability of an event is a fraction or decimal. It has to be between 0 and 1. 0 means the event is impossible, literally cannot happen. 1 means the event is certain, it's guaranteed to happen. Okay, most interesting probabilities fall somewhere between 0 and 1. Okay, this is the notation we use for probability. P of A means probability of A. And then P of A complement, that means the probability that event A does not occur. Okay. All right, odds. For those of you who like to go to Vegas or like to go to the horse track, they talk about casinos and horse tracks, race tracks, typically talk about odds instead of probability. Okay, so there's what's called the actual odds against, excuse me, the actual odds against an event is the ratio probability of A complement over probability of A. And it's usually written in the form A to B with a colon, where A and B are integers. Okay? And then it's usually reduced to simplest form. So if you had 16 to 4 odds, that's usually written instead as 4 to 1. It's just like how you reduce the fraction 16 over 4 to 4 over 1. Okay, it's just like that. Okay, so basically what the actual odds against tell you is how many ways are there for the event not to happen compared to how many ways are there for it to happen. So odds against are what you typically see at a casino. Okay. But there is such a thing as odds in favor, so that's just kind of, I guess it would be the reciprocal. You put the good number first and the bad number second. I say the good number for the number of ways you win, and then the number of ways you lose is the second number. Okay. So obviously, if you're going to a casino, it's important to understand, are you looking at odds against or odds in favor, right? You're probably looking at odds against. And then, unfortunately, casinos do not use actual odds. They use what are called payoff odds. So obviously, casinos are in the business of making a profit. They've got to keep their lights on and pay their staff and give the CEO big bonuses. So instead of using the actual probability that you win the game, they rig it a little bit in their favor so that, you know, if they play the game a million times, they're still going to come out ahead, right? I guess that seems fair. Okay. So the way you do payoff odds, and of course I have examples here, is the ratio of net profit to the amount bet. Okay. So if you would win $35, I think is the example we're going to look at, on a $1 bet, the payoff odds would be 35 to 1. Okay. And it's net profit because it's taking into account the dollar that you put down. So think of it as you get your dollar back. If you won a bet that had 35 to 1 payoff odds, you would actually get $36. You would get your original dollar back, and then you would get $35 more. Okay. All right, so here's an example looking at actual odds versus payoff odds. If you bet $5 on the number 13 in roulette, for those of you who are not familiar with roulette, it's a big wheel with a little ball on it, and they spin the wheel and they throw the ball down. The wheel spins for a little while, and eventually the ball settles down on some number. Okay? And the numbers that are used in roulette are the numbers 1 to 36, and then the number 0 and also double 0. Okay? And half of the numbers are red and half of the numbers are black. Okay? I don't think they get into red and black numbers in this example. Anyway, that's kind of how roulette works. So if you bet $5 on the number 13, your probability of winning is 1 over 38, because there are 38 different numbers. But your payoff odds are 35 to 1. Okay, so if you bet $1, you're actually going to get your original dollar back plus $35 more. Okay. So the first thing they want me to do is find the actual odds against the outcome of 13. And then they want to know how much net profit would I make if I win by betting $5 on the number 13. And then, if the casino was not operating for profit and the payoff odds were changed to match the actual odds, then how much would you win? Okay, so the first question was, what are the actual odds, not the payoff odds, but the actual odds against the outcome of 13? Remember, actual odds against are the number of ways it doesn't happen to the number of ways it does happen. So we know that the probability of getting the number 13 is 1 out of 38, which means the probability of getting anything else is 37 out of 38, right? There are 37 other numbers. So the actual odds against 13 would be the probability of not 13, which is 37 out of 38, divided by the probability of 13, which is 1 out of 38. And then if you simplify that expression, it simplifies down to 37 over 1. Just think if you multiply the top and the bottom of this big fraction by 38. Sorry for my messy chicken scratch here. This 38 will cancel this 38. This 38 will cancel this 38. And it'll leave you 37 over 1, which is usually written as 37 to 1. So the next question was, how much net profit would you make if you win by betting $5 on the number 13? Okay. So they gave me the payoff odds. The payoff odds were 35 to 1. Which means for every $1 that you bet, you get $35 net profit. So if I bet $5, then just multiply that 35 by 5. Okay. $35 profit for every $1 bet. So for a $5 bet, that would be 5 times 35, which comes out to 175. And remember, that's net profit, which means you get your $5 back. They give you your $5 back, which means now you're even. And then if they give you another 175, that's 175 in net profit. Okay. So the total amount collected would be $180. But their question was, how much is your net profit? So that the answer to that question would be 175. So that brings us to part C. If the casino was not operating for profit, and the payoff odds were changed to match the actual odds against the number 13, how much would you win if it came up number 13? Okay. All right, so remember in part A, we figured out that the actual odds against 13 are 37 to 1, because there are 37 numbers that are not 13 versus only one number that is. Okay. So that means if they were actually paying off, using these as payoff odds, they would be a $1 bet would get you a $37 net profit. Okay. So if you bet $5, your net profit would go up to $185. Okay. So think of it as, you know, the reason they only pay $175 is because they want to make $10. You know, if there are a whole bunch of bets like that they lose, and there would be over a certain amount of time, they still need money to keep their lights on and pay their people, and you know, so they can afford to give everybody free drinks and all that kind of thing. Okay. All right. But if they weren't worried about any of that, then they would pay $185 on a $5 bet. And you would walk away with your original $5 plus another $185.